All right, today we are going to crack a problem you see all the time in coding interviews, finding a little piece of an array that adds up to some target number. Now, it sounds simple, right? But the best way to solve it is actually pretty brilliant. So let's just dive right in.
So let's get our heads around this with a super simple example. Imagine you've got this array, 1, 1, 1, and our target, we'll call it k, is 2. Just take a quick look. How many different continuous chunks of that array add up to exactly 2? Yeah, you can probably spot them right away. But what if that array had a million numbers? That's when we need a real system.
You know, the first idea that pops into pretty much everyone's head is what we call the brute force approach. It's the most direct, most obvious way to think about it, but as you're about to see, it's a trap. It has a major weakness.
The logic here is, well, it's straightforward. We basically tell the computer, hey, check every single possible subarray. You pick a starting point, then you pick an ending point. You add up everything in between, and then you ask, does this equal our target k? If it does, great, we tick a counter up by 1. And you just do this for every single start and end combination you can possibly imagine.
Well, simple, yes. Slow? Oh, you have no idea. This method has what we call a time complexity of O(n)². Now, what that means in plain English is that if your array gets twice as big, the time it takes to solve it could get 4 times longer. For a tiny array, no big deal. But if you have an array with thousands of elements, you are going to hit that dreaded time limit exceeded error, for sure. So this is the real question, isn't it? We have to find a better way. Is there any possible way to solve this without checking every single combination? Could we maybe figure this out by looking at each number in the array just once? The answer is yes. And trust me, it's incredibly clever. And that brings us to the hero of our story, a concept called the prefix sum. This technique completely changes how we look at the problem, and it is the absolute key to unlocking a solution that is not just elegant, but also lightning fast. So what on earth is a prefix sum? It's really simple. It's just a running total as you move through the array. So for our little array, 1, 1, 1, the prefix sums would be 1 at the first spot, then 1 plus 1 is 2 at the second, and finally 1 plus 1 plus 1 is 3 at the very end. See? We're just building up the sum as we go along. And this is where the magic happens. This is the big insight. The sum of any subarray, say from some spot I to another spot j, is just the running total at the end of it minus the running total from right before it started. Think about that. It means we can find the sum of any chunk of the array instantly without having to loop and add everything up over and over again. It's a total game changer. Okay, so if we're hunting for a subarray that adds up to our target k, we can just rephrase the entire problem. We're not looking for a chunk of numbers anymore. Now we're looking for 2 points in our running total sequence whose difference is exactly k. Now watch this. With just a tiny bit of high school algebra, we get our big aha moment. If we know that k equals current sum minus some past sum, we can just flip that around to say some past sum equals current sum minus k. And this gives us a magic question we can ask at every single step. As I'm calculating my current running total, I just have to ask, have I seen a previous running total that happens to equal my current total minus k? If the answer is yes, boom, we just found one of our subarrays. Okay, but that leads to the next hurdle, right? We're zipping through the array, we're calculating our running total, but how do we know, like instantly, if we've seen that specific past total we're looking for? We can't afford to stop and scan through all our past totals every single time. That would just put us right back where we started, in that slow O(n)² world. Our hero, the prefix sum, needs a sidekick. And the perfect sidekick for this job is the HashMap. You can think of a HashMap like a helper with a perfect instant memory. As our prefix sum hero is calculating the running total, the HashMap's only job is to remember every single total we've seen so far, and just as important, how many times we've seen it. Now there is one tiny but absolutely vital trick to this whole thing. Before we even look at the first number in the array, we have to initialize our map with this entry, 0, 1. Why? Well, think about it. What if a subarray that equals k starts from the very beginning of the array? Its running total will just be k. So when we ask our magic question, what is current sum minus k, the answer will be k minus k, which is 0. By preloading our map with a 0, we're basically saying, hey, the sum before the array even started with 0, and we've seen that one time. This is the key that lets us correctly count those cases. Okay, theory is great, but let's actually see this dynamic duo in action. We're going to trace our original example, nums equals 1, 1, 1, with our target k equals 2.
and just watch the magic happen, step by step.
All right, let's walk through this. We start with our count at 0 and our map with just that special 0, 1 inside. First number is 1. Our new running sum is 1. We ask, what's prefix sum minus k? That's 1 minus 2, which is -1. Is -1 in our map? Nope. So we just record our current sum of 1 in the map. Cool. Next number is 1. Our running sum is now 1 plus 1, which is 2. Now we ask, what's 2 minus k? That's 2 minus 2, which is 0. Is 0 in our map? Yes, it is. Our map says we've seen a sum of 0 one time. So we add 1 to our count. The count is now 1. We update the map with our current sum. Last number is 1. Our running sum becomes 2 plus 1, which is 3. We ask, what's 3 minus k? That's 3 minus 2, which is 1. Is 1 in our map? You bet it is. We saw it one step ago. So we add 1 to our count again. The count is now 2. We're at the end of the array. Our final answer is 2, and that is absolutely correct.
You know, what's so beautiful about this whole thing is just how tough it is. It doesn't care if you throw negative numbers at it, or if your target is 0, or if the array is just full of zeros. The logic, that simple prefix sum minus k check, it holds up perfectly across all these weird, tricky edge cases. It just works. And the grand prize for all this cleverness? We did the whole thing in a single pass. We only had to look at each number one time. This gives us a stunningly efficient time complexity of O of n. We went from an approach that would crash and burn on big data sets to one that can handle them in a flash.
So what's the big takeaway here? This is so much more than just a trick for one specific problem. I want you to think of this as a powerful pattern. You maintain some kind of running state. In this case, it was our prefix sum, and you use a lookup map to instantly ask questions about the past. So the real question is, where else in your work or in other problems you've seen could this exact pattern be the elegant solution you've been looking for?